Democritus was a Greek philosopher who, over 2,000 years ago, predicted atoms and named atoms. The word atom means indivisible, and he thought that there were these particles that were the smallest possible particle in nature, and they are what made up everything else, and he called them atoms for atomos, which means indivisible, which now, of course, we know they're not, but that's how long ago the first person who thought of that idea. So what does organic mean to all of you?
Something grown without artificial pesticides.
Mm-hmm. In this class, when we talk about organic, what we're talking about is the original meaning of organic, which means carbon-based. So food molecules, with the exception of water, are carbon-based molecules. Biology is all carbon-based, and that's what the word organic means. There's a lot of different ways that we can represent molecules. Molecules are the smallest functional clumps of matter. Molecules can have areas of attractive charge, and these we call polar molecules, where one side is positively charged and one side is negatively charged. There can be areas where there is no strong attractive charge, and this is nonpolar. So some molecules are completely nonpolar. For the most part, we'll get into details. And then there are molecules that have elements of both nonpolar parts and polar parts. I'm going to give you an example of butyric acid, of a lot of different ways that we can represent molecules. So starting with the common name. Butyric acid is a fatty acid that was first found in butter, which is where the name butyric comes. Many words in science come from either something that where it was first found or the name of a person. So in this case, it comes from where it was first identified in butter. And so that's the common name we still use. Then the IUPAC is the International Union of Pure and Applied Chemistry. And that's a body that an important part of what they do is naming things. So they have conventions for naming molecules. And in the IUPAC naming convention, butyric acid is called butanoic acid. And there's three parts to butanoic. The but comes from butyric acid, and butyric acid has 4 carbon atoms in it. And so because of that, a molecule with 4 carbon atoms, the prefix but has come to mean 4. So but means 4 carbon atoms. The AN means that part of the molecule is all single bonds between the carbon. And the OIC in the end means that it's a carboxylic acid, which we'll talk about a lot. So we don't really even need the word acid on the end because since it's oic, we know it's an acid. But a chemist who somehow never learned what butanoic acid was could look at this name, butanoic acid, and know exactly how the molecule looked just from the name of it. We use ball and stick models. These are really helpful because, so here you can see the black balls are the carbon atoms. So you can see there are 4 carbon atoms. The white ones are hydrogen and the red ones are oxygen. And that's a convention a lot of people follow, not always, so you may see different colors in different diagrams. But the nice thing about the ball and stick model is it shows every atom, and you can see all of the atoms. In a really big, complicated molecule, you might not be able to see them all clearly, but it shows the structure of the molecule, and you can see exactly how everything works. The next one is a space-filling model. So a space-filling molecule represents what it might look like in space, how it occupies space, but you can see it obscures some of the structure and some of the atoms. So in some cases where it's more important that we kind of understand what the molecule looks like in 3 dimensions, we'll use a space-filling molecule, but more often you'll see the ball and stick model. Then we have a displayed formula. This shows every single atom, C for carbon, H for hydrogen, O for oxygen. You see the double bond between carbon and oxygen, and then all the rest are single bonds. In chemistry, we don't typically use the displayed model so much, especially for larger molecules. It gets really unwieldy. So instead, what we, especially in organic chemistry, we'll use the skeletal formula. This shows all the same information as the ball and stick or the displayed formula, but it's a lot easier. You can see it's a lot simpler and easier to read quickly. These lines represent carbon atoms. So if there's an endpoint with nothing else on it, that means there's a carbon atom here. Does anyone know how many bonds carbon forms? Anyone remember their high school chemistry? 4. So carbon form 4 bonds. So because there's one bond is here, we know there's 3 more bonds, and we know that those bonds, if it doesn't say that they're hydrogen. So we know that this is a carbon atom with 3 hydrogens coming off of it. Every kink in this is another carbon. So we've got a carbon here. There's already 2 bonds. So how many hydrogens are there going to be? 2. Same thing here, 2. In this case, we have a double bond with this oxygen, and we have a single bond here and a single bond here. So there's not going to be anything else here. And then here we have an oxygen atom that is at the end of this line. So if there's something here, then there's not a carbon atom. This means this bond is to the oxygen. Oxygen forms 2 bonds, so one is here and the other one is to this hydrogen. I don't expect you guys to learn or be able to read these easily, but it's helpful just to know what this means and to be able to look at it and kind of understand what's going on. We will look at some skeletal formulas in this class and use them. And this, what's called the functional group, the carboxylic acid, we'll see a lot. So if you don't remember anything else from the organic chemistry part of the class, please remember the carboxylic acid and what it looks like, because we're going to see that again and again and again. The other thing we'll see a lot, that occurs a lot, is an OH group, which is an alcohol group. There are a few things that you'll see so many times, they'll hopefully just start to stick. So those are all the ways that we represent molecules. And now we're going to kind of take a step back and look at kernel of wheat as a model for all of the different kinds of molecules that are in foods and in biology. Wheat has sugars and starches in it. Sugars and starches are very closely related, as we'll see. Water, fiber, proteins, fats and phospholipids, vitamins, minerals, and volatile compounds, odors. So we're going to go through all these one by one. In this lecture, this is just going to be an overview, and then in subsequent lectures, we'll dive into all of these a lot more deeply and explain them more comprehensively. So sugars and starches, we're going to start with the 3 most common and most important sugars, both in food and in biology: glucose, fructose, and galactose. So these are the smallest units that can still be called sugars. And because they're one group, this is one sugar group, glucose, fructose, and galactose, they're called monosaccharides. Mono meaning one, and saccharide meaning sugar. Now, you can take these single monosaccharides and link them together into larger molecules. If you put 2 glucose together, you get maltose. Maltose is the sugar that is, I'm sure you've all heard of malt, right? So malting is where you take a grain, usually barley, but it can be any grain, and you germinate it. So you put it in water, it just starts to sprout, and then at that point, they're typically dried, sometimes roasted, and then they're ground into flour. And when seeds just first start to germinate, they produce a lot of this sugar maltose. So malt has a lot of maltose in it. Sucrose, which is common table sugar, if you buy white sugar at the store, that's sucrose, is a combination of fructose and glucose. And then galactose, which is the sugar in milk, is a combination of galactose and glucose. So what's the common element in all of these disaccharides? Glucose. So glucose is a super, super, super important sugar in biology and in food. Now, the next level is starches. So starch, like in rice, bread, potatoes, any kind of starch that you eat, is a combination of 2 different molecules, amylose and amylopectin. And both of these molecules are chains of glucose. And when they link together this particular type of called alpha glucose, they form these helices, these spirals, and they're very, very long, much longer than this little diagram I made shows. So that's amylose, and then amylopectin is the same thing, except that instead of just being a linear single chain, it's a branched chain, so you end up with all these branches, but this also made just from glucose. And different foods have different ratios of amylose and amylopectin that we'll talk about, which gives them different properties. But these are all starches and starches made from sugar, so monosaccharides, disaccharides, and starches. So we're going to dive a little bit into a glucose molecule. As I mentioned earlier, molecules are all constructed from atoms. But I need to point out that you can't trust atoms because they make up everything. So white is hydrogen, black is carbon, and red is oxygen. So now we're going to dive into a carbon atom to show how atoms look as we zoom into them. So here we have a carbon atom. The middle part with the red and the blue balls is the nucleus. The red balls are the neutrons. They have no charge, positive or negative. The blue are protons. They are positively charged. And then the electrons that are around the outside are negatively charged. So this is a very simple, unrealistic diagram. In reality, the nucleus is very, very, very tiny, and there's a lot of space before the first orbital where the two electrons are going, and then a lot of space for the next orbital, which in this case is 4 electrons. But this is generally kind of the structure of it. So each of these circles that has the electrons is called a shell. And the first shell only holds 2 electrons, and then it's full. The next shell can hold 8 electrons, and then it's full. And the third shell, for all of the atoms that we're going to be talking about in this class, holds 8 electrons as well. As they get to larger molecules, it can hold 18, and it gets really complicated after that. But fortunately, we don't have to worry about any of that. So for you guys, just know the first shell is 2, the second shell is 8, and the third shell is 8. So every type of atom has a different number of protons. The number of protons in an atom is what defines that atom. So for example, hydrogen has 1 proton. Carbon has 6 protons, and oxygen has 8 protons. So if it has 8 protons, it's oxygen. And then here are all the other ones filling in. So helium's 2, lithium 3, beryllium 4, and so forth. They may have different numbers of neutrons in them, and they may have different number of electrons in them. It still doesn't change the fact that it's a carbon atom. So now we're going to zoom into hydrogen. Hydrogen is very simple. It's 1 proton, just positively charged, and 1 electron, which is negatively charged. And because this hydrogen atom has a positive charge and a negative charge, it's balanced. And so it's happy in that regard. However, it's got 1 valence electron, and how many does the first shell hold? 2. And it wants to have 2, and it only has 1. So it's happy that it has equal charge, but it's unhappy because its outer shell is not full. Now, if we look at a hydrogen molecule, that is 2 hydrogen atoms that are sharing their electrons with each other. So now we have a molecule that has 2 protons positively charged, 2 electrons negatively charged. So the charge is balanced, so it's happy about that. And both of the atoms have 2 electrons in their outer shell because they're sharing them. So now the outer shell's full for both of them, and so they're happy in that regard. So this is a very stable, happy molecule. When we look at the ball and stick model, the sticks in them are this covalent bond. The word valent means power, and the outer shell of the atom that has electrons is called the valence shell. So covalent means that it's the sharing electrons between 2 different atoms. And we represent that with this stick. So To summarize, sugars and starches. They're made up of monosaccharides, such as glucose, fructose, and galactose, glucose being the most important monosaccharide. They can be monosaccharides, 1 unit, or disaccharides, 2 units. And monosaccharides and disaccharides together are what we call simple sugars. So if they have any more than that, they're no longer simple sugars. Molecules are unique functional clumps of matter made from atoms. We have 118 known atoms that we call elements, and each one of those has a different number of protons, which is what defines it as that atom. Some of these are very unstable and they've been created in a lab, but they have very short decay, and so they won't live for very long. And there are many that we have never found in nature, but these are ones that either we found in nature or that we've created in a lab. They're made from neutrons, protons, and electrons. And remember, again, neutrons have no charge, protons have a positive charge, and electrons have a negative charge. They want to have their outer shell full, so they will share electrons with other atoms in order to achieve that and still have a balance of positive charge with negative charge. And also, remember again, the first shell holds 2 electrons, the second one 8, and the third one 8. Hydrogen has just 1 proton and 1 electron, and because it wants to have 2 in its outer shell, it will form a bond with another atom to fill its outer shell. Hydrogen forms bonds with lots of things, and we'll see hydrogen a lot in organic chemistry. Bonding with carbon, bonding with oxygen, bonding with sulfur, all kinds of things. All right, now we're going to move on to water. So here is a representation of a water molecule. This is an oxygen atom and 2 hydrogen atoms. This little weird squiggly thing is a lowercase delta, a Greek letter delta, and this letter means a partial charge. So an electron is a full negative charge and a proton is a positive charge. In this case, because they're sharing electrons, this has a partial positive charge, so it's not completely +1 charge, and the oxygen side has a partial negative charge. And because this is charged positively here and negatively here, this is a polar molecule, so it can attract other molecules. Water is a fascinating and really, really important molecule. Life as we know it would not be able to exist without water. We call it the universal solvent. It's not truly universal, but almost everything can dissolve in water to some extent. Because it's polar, the charge, the positive and negative charges on it can pull, like for example, if you put salt into water, salt is an ion made up of a positively charged molecule, or ion actually, and a negatively charged ion that stick together because they're attracted to each other as well. So the attraction from water will pull an ion of salt off of it, and it's also because they're smashing into each other, that's what causes salt to dissolve. And the same thing happens with most substances. If they're solids in water, the polar nature of water will pull them apart and dissolve them. Water lubricates and cushions in biology. It has a very high surface tension because, again, of the polar nature of the molecules. So if anyone's ever done a belly flop, you know this from personal experience. There are those little skeeter bugs that can walk around the surface of water. It provides structural support. It helps regulate temperature. Water has a very high specific heat, which we'll learn about. But what it means is that water can hold a lot of heat, much more than most other substances. And so because of that, it's very stable. So in our bodies, because we have so much water, it takes a lot of energy or loss of energy for our temperature to go up and down. So it really helps stabilize our homeostasis of temperature. It's also a medium for biological processes. So biological processes, our metabolism and enzymes, taking things apart or putting them together or doing other things that they do, happen in water. It also provides a transportation medium for nutrients and waste, so our blood, plasma, for example. And it's a key element in most biological chemical reactions. Water is not only a medium for the reaction, but the water molecules themselves are actually really important in how the reactions happen. And we will see that in lots of chemical reactions, they involve a water molecule becoming part of the reaction that forms or puts together or takes apart other molecules. So here's a water molecule, here's our glucose molecule. We see here all the covalent bonds between them in this ball and stick model. If these bonds are between different types of atoms, like hydrogen and oxygen, because the oxygen has a bigger nucleus with more positive charge in it, it's going to attract the electrons more closely to it. And because the electrons are closer to it, electrons have a negative charge. That means that the oxygen side is going to have a stronger negative charge. That's why we end up with the partial negative charge on the top of the oxygen, and the hydrogens that aren't as strong and they don't have the electrons around them as often will lose some of that negative charge, so it doesn't fully balance the positive charge from their one proton. Here we have the model of oxygen. I haven't drawn all the protons in here, but we've got 2 electrons in our first shell, and we've got 6 in our outer shell. So it wants 2 electrons in its outer shell. After it fills the first shell, which it always fills first, it's going to fill its second shell with electrons. With 6, it can hold 8, and so it wants 2 electrons. So hydrogen, that has an electron, and it's trying to fill its outer shell as well, will share an electron with the oxygen, and that fills its shell, and it gives it 7 to the oxygen, and then the second hydrogen does the same thing, and it gives now 8 to the oxygen, and it fills its shell. So it's all electrically balanced, and it's all balanced in terms of everyone's shell being full. So it is stable and happy in this way, and this is why water molecules form like this. There are 3 different types of ways that electrons are shared in covalent bonds, or in general. One is a covalent polar bond. So remember, polar means that they're not shared evenly, and so there's going to be a difference in charge on one side versus the other. So here is hydrogen and chlorine, and so when they bond together, the chlorine is going to occupy, or the electrons are going to be around the chlorine more of the time than they are the hydrogen. So same thing like we just saw in water. This will have a slight negative charge, and this side will have a slight positive charge, so it's covalent because they're sharing, and it's polar. If you have 2 of the exact same atoms, then they have the same pull on the electron, so they're going to share equally. So it's still a covalent molecule, but it's nonpolar because they're even sharing, so there's not going to be a charge on either side. And then the last one is, rather than a covalent bond, it's an ionic bond. And this happens in salts, for example. Sodium chloride is table salt. So here we have sodium, which has a very weak pull on electrons. And we have chlorine, which has a very strong pull on electrons. So rather than sharing electrons, the chlorine actually completely takes the electron from sodium. So now sodium has a full positive charge because it's lost its electron, which is negative. Chlorine has gained a full electron, so it has a full negative charge because it has an extra electron more than the number of protons it has. So this is not a molecule. These are now 2 ions, but because this is positively charged and this is negatively charged, they're going to stick together. It's not a magnetic charge, but it's very similar to the way a magnetic charge would work with a north pole and a south pole. So what holds water together? I want you to think about these questions, and then we will address them in a couple minutes. So why is water a liquid at room temperature, but air is not? What causes water to hold together in drops? What's heavier, air or water? And what causes rain to fall from the sky? So the reason for all of these things is hydrogen bonds. So we just talked about how The oxygen side of the molecule has a negative charge, and the hydrogen sides both have a slight positive charge. And those are going to be electromagnetically attracted to one another. So the slight positive here will have a attraction to the negative here. This is called a hydrogen bond. They're called hydrogen bonds because this doesn't have to be oxygen necessarily. It could be some other atom. But the hydrogen, which has a very weak pull, will have a positive charge. So there's going to have this attraction here towards each other. So again, kind of like magnets attracting each other. And this hydrogen bond is a super important bond for all kinds of things in chemistry and food and life. And this accounts for all the things that we just talked about. Why is water liquid at room temperature, but air is not? So air is primarily oxygen, which is a nonpolar molecule, doesn't have that charge, and nitrogen, which is also a nonpolar molecule, which doesn't have that charge. Because those molecules don't have that attractive charge to each other, they don't stick together very easily. So they're happy on their own. Water, on the other hand, has a very strong charge that attracts them together, so they will tend to stick together a lot more easily. When they stick together, that's what makes water, as opposed to water vapor in the air. What causes them to hold together in drops? Again, it's the same thing. The hydrogen bonds are very strong, and if you watch a drop of rain fall in slow motion, we think of it as a teardrop, right? But it's actually a sphere, pretty much, because they're very small. They have very high surface tension, so they're going to drop in these spheres because all of these molecules are sticking together so strongly. What's heavier, air or water? Air is heavier than water, actually. So you think that water is heavier because you think of water as, a bunch of water together. But water molecules are actually lighter than air molecules are. So that is what allows them to evaporate, go up into the atmosphere. And then in the atmosphere, rain is a little more complicated than this because there need to be nucleation sites for the rain to kind of start the drops. But what ultimately happens is two water molecules, if they stick together, they are now heavier than. So once enough of them stick together, they get heavier and heavier, and then they fall from the sky because then they're much heavier than the air is. So all of this, again, goes back to hydrogen bonds. So I want to talk about state change and chemical change. So this is water as an example. If we have liquid water and it evaporates, or if it evaporates, it's called evaporation, surprise, surprise. So when it evaporates, it's called evaporation. When a gas goes back to a liquid, it's called condensation. When water freezes, we call that freezing, and when it becomes a solid, I guess I should say, when it turns from a solid to a liquid, we call that melting. But there's another thing that people often don't think about or don't know about, which is that solids and gases a solid can go directly to a gas, and a gas can go directly to a solid. So when it goes from a solid to a gas, it's called sublimation, and when it goes from a gas to a solid, it's called deposition. And we'll see examples of sublimation. So this is state change, going from a liquid to a solid to a gas. The water molecules are still water molecules. There's not changing the nature of the molecules. It's just changing how closely they're sticking together and in what way. When water becomes a solid, it forms a crystal structure. And water is the only molecule that does this, which is when it becomes a solid, because of the way the crystal structure works, it expands slightly. So when water is about 4 degrees Celsius, that's the most dense that it becomes. And then as it starts to get colder and freeze at 0 degrees, it becomes bigger. And because of that, ice is less dense than water, and that's why ice floats in water. Here, on the other hand, we have chemical reactions. So we have, on the right hand, we have water molecules. On the left hand, we have hydrogen molecules and oxygen molecules. So sometimes when these molecules bang together with enough force and position the right way, 2 oxygen atoms and the 4 hydrogen atoms, the hydrogen atoms might glom onto the oxygen and break the bonds, and so we'll end up with water molecules rather than hydrogen and oxygen. So we have the same number of atoms of each type on each side of the equation, but they're completely different molecules that have different properties from each other. So that's a chemical reaction. So in summary, water has a lot of functions that make life possible. It acts as a medium for biological processes. Both the inside and the outside of your cells is mostly water. Water helps organisms transport nutrients and waste products. It's a part of a lot of chemical reactions, especially in food and biology. Water molecules are made from 2 hydrogen atoms and 1 oxygen. Oxygen has 6 electrons in its outer shell, but it wants 8 to fill its shell. So it shares electrons with 2 hydrogen atoms. Its outer shell gains those 2 electrons. So it has 8 and hydrogen gains 1 each. So it has 2 filling its outside shell. Water molecules are charged molecules. So both of the hydrogens have partial positive charges and the oxygen side has a partial negative charge. So that makes it polar. And so because it's polar, it will be attracted to and it will attract any other polar molecule or part of a polar molecule. This electromagnetic pull between these molecules creates these bonds that are much weaker than covalent bonds, but they're much stronger than some other types of bonds that we'll see. And they're called hydrogen bonds because they involve hydrogen on one of the molecules. And matter can be solid, liquid, or gas, and changing the phase does not change the molecule. So those are 3 phases of matter. Those are the ones we talk about the most. There are actually 5 phases of matter. Does anyone know what either or both of the other 2 are? Plasma is one. And the other one is the Bose-Einstein condensate, which happens at temperatures very close to absolute zero, where I can't really explain it without getting a lot into physics, but things get very weird, I'll just say. All right, so next we're going to talk about fiber. And we're going to, since we're talking about wheat, we're going to kind of zoom in to what fiber looks like in wheat. If we look at part of the cell wall and we zoom into it, we see cellulose. Cellulose is made up of microfibrils that are in different directions across each other, which gives it a lot of strength. If we zoom into the microfibril, just one of them, then it is made from all of these cellulose molecules, which are these very long, straight molecules. And if we zoom into what those molecules look like, they are chains of a type of glucose, which is different from, it's glucose like starch is glucose, except it's a beta version of it. So there's a slight change we'll look at later, which changes the way that they link together and makes them straight rather than helix. And because of that, they can get very close together. And because they can get very close together, the hydrogen bonds that we just learned about, those electromagnetic bonds, bond these very strongly together. So that's what gives cellulose all of its strength. So cellulose, pectin. Pectin is a molecule that's made out of a different sugar molecule we'll look at later. And other fiber molecules are all found in wheat. Cellulose is the most abundant organic polymer on Earth. And because it's made from glucose, glucose is the most abundant, whether by itself or as a disaccharide or with sucrose or with cellulose. There are more glucose molecules than any other organic molecule. As I just mentioned, cellulose forms these very long straight chains, and they stick together very strongly and form very strong fibers. Next, we'll talk about proteins. Proteins are these long chains of amino acids, and I have represented them here with these little candies. Beads on a string is usually what people talk about as a model for what proteins are like. So you can think of these as beads that are connected on a string or little candies that are connected on a string. So every one of these is an amino acid. And there are 20 different amino acids in pretty much in all of nature. There are some nuances to that we'll talk about later. But any plant or animal, all the proteins are made from these 20 amino acids in different combinations. These are the 3-letter codes for alanine, glycine, leucine, methionine, valine, and they also have 1-letter symbols for all 20 of them. And so you can kind of think of it like an alphabet, and like an alphabet like in English, some of these letters or some of these amino acids occur a lot more commonly than other ones do. And these chains, proteins, can be as few as 50 amino acids long, or they can be thousands of amino acids long, but it's still just one long chain. In trying to figure out a good analogy for this, I came up with this, and this is the best I could do on the drawing of it. The way that they chain together is that they have arms kind of that hold onto each other, and the left arm is different from the right arm, but they're the same on all of them. Every amino acid's right arm is the same as every other one, and their left arm is the same as every other one. And their head unit, which is actually hydrogen, is the same on all of them as well. What's different is the legs. And so here we have R and R, which is arginine. So their legs are the same. And then here we have glycine, and their legs are the same as each other. And it's their legs that are what determine whether they're acidic or basic, or they have a charge or don't have a charge. There's a lot of different attributes of the way their legs are that determine the way proteins fold and interact with each other. So that's the basic structure. We'll learn about it in a little more detail. But that's basically how proteins work. And proteins can fold and work in different ways. So there's 2 main types of proteins. There's structural proteins, which are fibrous proteins. So here I have 2 little candies wrapped around each other. Keratin, what your hair and skin and other stuff is made of, looks very much like this. There are 2 chains of proteins wrapped around each other. And then there's globular proteins, which form these balls. And globular proteins are functional proteins. So they are the proteins in your body that actually do things. Like enzymes, for example, are globular proteins. Enzymes are fascinating, super versatile proteins that kind of run everything biology. And we'll see some examples of them. They're really, really, truly fascinating. But they are basically these balls of this one long string of amino acids, and it's the shape of the protein that determines its function. So here we have our periodic table. We're not going to go into this in too much detail or use it too much in the class, but I did just want to point out a few things. First of all, different atoms have different electronegativity. Electronegativity is how, remember I talked about how oxygen will pull the electrons to it a lot more strongly than hydrogen. So as we go up to the upper right, not talking about helium, and the noble gases are a little bit different, but like fluorine, they're more electronegative as we go up to the upper right and less electronegative as we go down to the lower left. So if we zoom in on carbon, this periodic table is from ptable.com, which is a free website, which if you're interested, is a great site for just tons and tons of information, really nicely done. It's a great site for the periodic table. So here we have carbon, and I just want to kind of point out what all these numbers and stuff mean. Number 1 is the atomic number. Hydrogen is 1, that's 1 proton. Helium is 2 protons, lithium, beryllium. So that's what's going to determine, remember, it's the number of protons is what determines what type of atom it is. Then we have the symbol, and often it's either 1 or 2 letters, and often it's going to kind of make sense, like C for carbon, N for nitrogen. There are some cases like Pb for lead comes from the Latin, so in some cases it may not make a lot of sense, but in most cases it's pretty easy. Then we have the common name that we call it, and then the atomic weight. The atomic weight, there's a term that you might run across called a Dalton. You will definitely run across it because I use it sometimes. And the atomic weight is based on carbon-12, which is the most common isotope of carbon. And carbon-12 has a weight of exactly 12. So that defines everything else. So why is this not exactly 12? Does anyone know?
Did they like average all the other types of carbon, like carbon 13?
Yeah. So they average all the isotopes. And there are very few of the other ones, but there are some. And so the average of them is not going to be exactly 12. And you'll see that in a lot of places. Sometimes, like, in chlorine, this is almost 35 and a half. So you can see by that there are two different isotopes there. And then the last thing that this periodic table shows is the energy levels. So the first shell, which is full, holds 2. It has 2. The second shell, which again holds 8, has 4. So just by looking at that number, we can determine how many bonds it will typically form. Now, if we expand this a little bit and we look at hydrogen, carbon, nitrogen, and oxygen, hydrogen has 1. So the first shell holds how many? 2. So how many bonds will hydrogen form?
2.
1. Because it already has 1, so it will form 1 bond. Carbon has 4. We've already talked about this a lot. So how many bonds will it form?
4.
And how many bonds will nitrogen form?
3.
And oxygen?
2.
Okay. Now, I picked these out specifically because these are the 4 elements that are by far the most common in all life and food. So if we look at the percentage of all of these atoms, 63% of the atoms in your body are going to be hydrogen. Almost 10% carbon, just a little bit of nitrogen, but super important. And then about 25% of oxygen. So altogether, 99.4% of all the atoms are one of these 4. Other important ones are sulfur. We'll talk about sulfur a lot. So one reason that sulfur is so important is because it forms a particular type of bond that's really important in proteins, called a disulfide bond. Sulfur has 2 in its first shell full, 8 in its second shell full, 6 in its third shell. Remember, again, at this level, before we get into the higher ones, this third shell will hold 8. So sulfur will form how many bonds? 2. All right, so in summary, proteins are very long chains of amino acids, between 50 and thousands. 50 is sort of an arbitrary number. Sometimes you'll see 100 in some texts, but there can be chains of amino acids that are fewer than 50, but it's too small for them to function as a protein. And so we call them peptides instead. A lot of hormones are peptides. Some hormones are proteins. In the case of hormones, we call them all peptides just because it's easier, whether they're technically proteins or have more than 50 or more than 100. And a lot of hormones are a derivative of a single amino acid. So again, that's sort of an arbitrary number, but larger than that, they're big enough to actually function the way a protein does, which we'll talk about what those functions are. Our bodies, and not just our bodies, but in all of nature, there are 20 different amino acids. Each one has different properties. And it's the forces between the amino acids that cause the proteins to fold into a particular shape. And it's the shape of those proteins and the forces of the charges on some of the amino acids in the protein that determine the way that the protein functions. Over 99% of atoms in food are hydrogen, oxygen, carbon, and nitrogen. Carbohydrates and fat, so sugars, starches, cellulose, pectin, don't contain any nitrogen. But nitrogen is a super important part of proteins. And we'll talk about this both in our proteins lecture and in our nutrition lecture. Because it's only in proteins in our diets, that is why we need to eat protein to create other proteins. Your body can make fats out of carbohydrates or vice versa. It can burn. Glucose is the most important sugar that our body uses as fuel, but it can use other sugars, it can use fat, it can use proteins as fuel, but it can't create nitrogen without nitrogen, and it can't create proteins from the other food molecules. And then sulfur is also an important component of proteins, and it's found in 2 of the 20 amino acids. Cysteine being the one we'll talk about the most. Next is fats and oils. So fats are built from long hydrocarbon chains that we call fatty acids. And these molecules, the hydrocarbon part of it, are nonpolar. So they're not charged like water molecules are. So they don't have that strong attractive force like water molecules and sugar molecules and salt because they're nonpolar. Now, I say sort of because they actually have a little bit of charge, and that's really important, and we'll talk about that and how that works, but most people consider them completely nonpolar. So if we look at the structure of fat, then you have 3 different fatty acids. So this carboxylic acid group in the end is going to bond with part of the glycerol backbone, and we have 3 of them, and that's what makes up a fat. The 3 fatty acids can be all the same, they can be all different, they can be shorter or longer, they can be straight or kinked, or all different ways, but all fats and oils or fats are going to look like this. Phospholipids are very much like fats. They have the same glycerol backbone, and the glycerol backbone has 3 places that can attach to other molecules. But unlike fats, instead of having 3 fatty acids, they only have 2. And the last spot that glycerol can bind to, instead of binding to a fatty acid, binds to a phosphate group. So fatty acids are nonpolar, so they're not going to be attracted to water, sort of. And they will be attracted to other fats. The phosphate group, however, is polar. So this will be attracted to water. And because of this, you can use this phospholipid to mix water and oil together. And when you use an egg yolk and make salad dressing out of it, that's exactly what's happening. The egg yolk has a lot of these phospholipids in it, and so part of this molecule will attach to fat and part of it will attach to the water, and that's what allows it to combine together. So this is what we call an emulsifier. And it's also super, super important in biology, and we'll see that as well. So now, fat molecules are not polar, so why are they liquids and solids at room temperature? Why are some liquids and some solids? What makes something a solid is how strongly the molecules stick together. If they stick together really strongly, then it's going to be a solid. If they stick together very loosely and they kind of move around, then it's going to be a liquid. So fats, and what we call a fat when we're talking, in cooking, we mean something that's solid at room temperature. If it's an oil, that means it's a liquid at room temperature. But fats and oils structurally are exactly the same. The only difference in them is how sticky they are. And the stickiness has to do with 2 things. One is the length of the fatty acid chain. The longer it is, the stickier the fat's going to be. And the other one is whether that fatty acid chain is straight or kinked. Remember when we talked about cellulose molecules, the reason they stick together so strongly is they're very straight. So long, straight fatty acids have a lot of areas where they can get very close together and have those bonds that bond them together. They're not hydrogen bonds. We'll learn about the type of bonds in fats, but it's the same electromagnetic force. It's just a very weaker version of it for different reasons. So that's why some are liquids and some are solids. Why don't fats and water mix? A term that you'll hear a lot in food science and not in food science is hydrophilic and hydrophobic. Has anyone heard of these? So hydrophilic means, hydro means water and philic means loving. So hydrophilic are molecules that love water and they cling to water. They're attracted to water. Hydrophobic means scared of water, and these are molecules that don't bond to water, like oil, for example. I don't like the word hydrophobic because fats are not scared of water, but they're also not repelled by water. And there are very few food science textbooks or anything that really explain this correctly. What actually happens is not that, because fat, if you have a single fat molecule in water, it will be attracted electromagnetically with the water. But what happens is that water molecules have such a strong attractive force to one another they exclude the fat. They kind of push it out because they would rather bond together than bond with the fat. And that's why water and fat separate. So now we get to talk about van der Waals forces. This is another term you will see in almost every text or any class or anything you take. They'll talk about van der Waals forces. Van der Waals forces are actually a category of forces that include London dispersion forces, Debye forces, and Keesom forces. And when people talk about van der Waals forces, what they really mean usually is London dispersion forces.
Lambert, what is the length of the comfy down, Majorette?
2 foot long.
2 foot long? Yes, you have to remember, of course, to multiply everything Mr. Lambert says by 3. It's nothing he can help you understand. Apart from that, he's perfectly all right.
Oh, I see, I'm sorry.
But it does mean that when he says a bed is 2 foot wide, it is in fact 60 feet wide.
But because everyone uses this term, I'm going to go ahead and use this term in this class. But just know that it's not really technically correct. For example, hydrogen bonds that we just learned about with water are, by some definitions, a type of van der Waals forces. They're much stronger than typical van der Waals forces. Some scientists will categorize them separately, but they are technically a type of van der Waals force as well. So, nonpolar molecules, and so these are fatty acids that we're looking at. This is a space-filling model of the fatty acids that we just talked about. They are attracted to each other through these very, very weak forces called van der Waals forces. And we learned about how in a water molecule, they're sharing electrons. And because the oxygen is pulling on those electrons so much more strongly, they're not in orbit. We'll talk about this more, but they are surrounding the nucleus of the oxygen atom, part of the water molecule, more than they are around the hydrogen. And because they're negatively charged, that gives the oxygen a partial negative charge. Here, because of the way hydrocarbons work, they don't have that polar nature. It all kind of balances out, so there's not this charge. But if you were to slow down time super, super slow, imagine an electron, and we're going back to the model where we imagine electrons orbiting like a moon orbits a planet, which again is not what really happens, but just pretend for now that it does. So let's say there's an electron orbiting here, and when its orbit is closer to the carbon atom here, then there's going to be the negative charge from the electron here, which, because there's a proton here with a positive charge, that will give this, for a very, very, very brief portion of time, a slight positive charge. And so because of that, there are these very small, transient, fleeting forces that happen. And so there's a very small charge that occurs that attracts these together. And if there's a very small positive charge here, that's going to attract the electrons here a little bit more. And so they'll end up being attracted to each other. So that very, very weak force is what we call van der Waals forces. And that is super important in how a lot of molecules, but fats in particular, what we're talking about now, that's what causes them to stick together. So did anyone see the movie Bug's Life? Remember the scene with all the ants and the grasshoppers? So it's the same kind of thing here. They're very, very weak forces, but there's a lot of them. So they add up and they make a little stronger force. They're still pretty weak, but it's strong enough to do a lot of interesting things. Because they operate at very close range, if these molecules can get close enough to each other, the closer they are to a point, the stronger the forces will be. If these molecules are very straight, that means that they can get very close to each other. So here we have stearic acid. It's this very straight molecule. And because it's very straight and they can get very close together, stearic acid melts at 157 degrees Fahrenheit, which is pretty hot, right? That's hot enough that if you put your hand in water, that you would be very uncomfortable and you would burn your hand. Now, oleic acid, which is the exact same, so this is 18 carbons. Oleic acid is also at 18 carbons. Everything about it is the same as stearic acid, except that there's a kink in it. And because of that, they can't get as close together. So oleic acid melts at 55 Fahrenheit, which is pretty cold, right? So this is what determines the length of this fatty acid, and how close they can get together is what determines how sticky they are. So next thing I want to talk about is redox reactions. Redox is short for reduction oxidation. It's very important in organic chemistry and in biology and in health and nutrition, but it's confusing to a lot of people, so I want to just try to explain it simply so you sort of understand what's going on. Oxidation means the loss of an electron. It's called oxidation because often involves oxygen. Oxygen is very electromagnetically strong, and so it can steal an electron from someone else. So if I'm oxygen and you got an electron and I steal it from you, then you have been oxidized. All right? Reduction is the opposite thing. Reduction is the gain of electron. The name is a little confusing because of how it was named historically, which we won't go into, but the way I like to think about it is that the charge is reduced. So if I'm oxygen again and I've stolen an electron from you, you've been oxidized, but I've been reduced because the electron is negatively charged, right? So I now have my charge has been reduced by 1 because I've added a negative charge to myself. Does that make sense? So that's oxidation and reduction. And if you forget an acronym that you can use, and there's some other ones you'll find out there, Leo says GER. So Leo the lion, LEO, loss of electrons is oxidation, and GER, gain of electrons, is reduction. There's also oil rig that sometimes people use. You can also just remember what I told you, and then you don't have to worry about the acronyms. Redox reactions always happen together. So if I steal an electron from you, I'm being reduced and you're being oxidized. It always happens at the same time because someone is the recipient of the electron. Oxidation is something that we have to worry a lot about in foods and in biology. Oxidation of molecules usually wrecks them. So oxidation is usually a bad thing. Lipid oxidation, lipid is a category of molecules that includes fats and phospholipids, and there's lots of other types of lipids we'll talk about. So flour, whole grain flour like whole wheat flour, nuts, which have a lot of fat in them, cocoa butter, which is all fat, regular cow butter, and lots of other animal fats, cooking oils and stuff. The fats in them can and do get oxidized, and so this is called rancidity. If we say something's gone rancid, then we are specifically talking about the fats in it, the lipids in it, and it's oxidative rancidity. It's the fatty acids have been oxidized. There's a different type of rancidity that we'll talk about later, but this is the more important and more common one that you'll hear about. Red meat can also become oxidized. That's myoglobin is the protein that makes red meat look red. And so when red meat is oxidized, it turns brown. And it will also, if you've ever smelled rancid fat, right, it smells bad, it tastes bad, and it's going to be bad for you to eat as well. So we want to stay away from that and take care of our oils and our fats. Same thing with red meat. If there's a lot of oxidation on it, it's not going to taste as good, and it could have, if you eat a lot of it, eating a lot of red meat has all kinds of health ramifications, but oxidized molecules generally are going to be bad. There is enzymatic browning. So here we have a picture of an apple where part of it has browned. So apples, potatoes, avocados, these all turn brown when they're exposed to oxygen. But it's an oxidation reaction, but it's sped up by a protein called an enzyme. We'll talk a lot about enzymes, but enzymes, again, are proteins that speed up reactions. So when you cut an apple, you're exposing the apple to oxygen, and there are enzymes in the apple that speed up this browning reaction. The pigment the brown pigment in apples is a melanin molecule. So it's very closely related to what's called eumelanin, which is the pigment in our skin that makes us brown. So it's a very closely related molecule that's making these guys brown as well. And then the last one is, rather than oxidation, it's reduction. And there's a molecule in fish called trimethylamine oxide, and it can be reduced to trimethylamine, which when you have fish that's old, that kind of smelly fish smell is because of the reduction. And so fish use this molecule, especially cold water and deep water fish, because it protects them from the cold and it protects them from the really intense pressure of being very deep. So if you have a fish that swims in very deep cold water, it's going to have a lot more of this molecule, and it's going to be a lot more subject to that fishy smell. So these are just a few examples of oxidation and, in one case, a reduction reaction in foods. And as I mentioned, they happen simultaneously since one molecule is oxidized and the other one is reduced. We call them redox, which is short for reduction oxidation. Iron, when it rusts, is also an oxidation reaction. So the iron is oxidized, it loses electrons to the oxygen, and the oxygen is reduced. Here we have some red ox, and I wanted to show an example here of salt, which we've already talked about. So when the chlorine atom steals an electron from sodium and becomes chloride, now it has its outer shell full. Sodium only had one electron in its outer shell, so it's very happy to get rid of it because now its new outer shell, its inner outer shell is now full. So that's why that happens. So here there's no oxygen involved, but this is still an oxidation reduction reaction. All right, so who's heard about free radicals? So I'm going to talk about free radicals. So a radical is an atom or a molecule that has one or more unpaired electrons. And they can be positively, negatively, or neutrally charged. Usually they're negative or neutrally charged. And because it has an unpaired electron, it wants to fill its outer shell, like electrons do. And so radicals can steal an electron from another molecule or atom. Free radicals are radicals that are very highly reactive and will very strongly and easily steal an electron from another molecule. So because, as I mentioned earlier, when a molecule gets an electron stolen from it, it changes the molecule, and usually in a bad way. And so for us, for our health, if we eat things that have free radicals in them, it's going to damage molecules in our body, which will damage our cells. In some cases, it can make us sick in lots of different ways. So that's what a free radical is. Now, an antioxidant is a molecule that's very stable, that can donate an extra electron to a free radical without becoming unstable itself. That's why we eat foods with antioxidants, because we always have free radicals. No matter how well we try to eat, there's always free radicals in our body. So by eating antioxidants as well, it's going to allow these free radicals to get its unpaired electron filled in without damaging any of the molecules that will get damaged by that reaction. Hydroxyl is a very common and very nasty radical that occurs a lot in nature and in our diets, especially with certain foods that you might eat or cooking methods. So that's an example. This is what used to be a water molecule, but it's missing a hydrogen and it's become oxidized. So it's not only lost the electron, but it's also lost a hydrogen, which sometimes happens in an oxidation reaction. It may be more than just the electron that gets pulled off. So in summary, fats are 3 fatty acids that are connected to a glycerol backbone. Fats are not water soluble, so they will clump together away from water. And the longer and straighter the chains are, the more sticky they're going to be. That stickiness is caused by van der Waals forces. Phospholipids are identical to fats, except that instead of 3 fatty acids, it's 2, and the last sort of slot on the glycerol backbone has a phosphate group on it, which is a polar part of the molecule. So that can attract water, and then the fatty acids can attract other fats. And we use that for an emulsifier for all kinds of stuff in food and cooking to allow fats and water, things that are what we call immiscible or unmixable, to be able to mix together nicely. Redox reactions are reactions where an electron is stolen from a molecule by another molecule. The molecule that takes the electron is reduced because it's taken a negatively charged electron and reduced in charge. The one that loses the electron is oxidized. Oxidation reactions change molecules. It can change their color, their smell, their taste, and their function. Iron turns red, for example, when it oxidizes, and fats who get oxidized become what we call rancid, and they smell and taste bad. And then last, free radicals are molecules that have a very strong need for an electron, and because they have that's very strong affinity for it, they can cause these chain reactions that not only damages one molecule, but that molecule now turns into a free radical, and it will damage another molecule, which will turn into a free radical, which will damage another molecule. And it can go on and damage lots of molecules just from one free radical. So now, what are vitamins?
We can't make them. Oh, that's vitamin D.
Okay, that's a very good answer. And vitamin D is also a very astute exception. So yes, vitamins are molecules that we need, that our body needs to function properly, that we can't synthesize ourselves, or at least in the required amounts. Vitamin D is produced in our skin, but not in the amounts needed for our health. And vitamin D is also interesting because it's a hormone as well. So there are 13 human vitamins. All different animals are going to have their own vitamins, not necessarily the same as humans. And a lot of these vitamins are actually groups of different molecules. So like vitamin E, for example, there's two major kind of classes of vitamins that make up vitamin E, and there's different examples of them. Some vitamins are very specific. It's just one particular molecule. But the thing with vitamins is if you are missing a vitamin, you will have a very specific disease that you will get because your body doesn't have that vitamin that it needs for some purpose. Here's an example of raisin bran, and one of the ingredients is mixed tocopherols. You'll see that a lot. The reason that they use the tocopherols, which is one of the two groups of vitamins, of molecules in vitamin E, is because it's an antioxidant. Another group of substances that our body needs are minerals. And there are a lot of minerals that our body needs. So here's an example of iron. This is a porphyrin ring, which is, I know it means nothing to you, but it's a structure that is common in nature in different ways it's used. And it's what's called a prosthetic group, which is part, when you have a protein, sometimes it will attach on another molecule to it to help it function in a particular way. This is a prosthetic group for hemoglobin to oxygen. This is how oxygen is carried through your body. So it's kind of a complicated set of things that happens, but without the iron, your body wouldn't be able to transport oxygen. Here is the same molecule, another porphyrin ring, but in this case, instead of iron, it's magnesium. And this magnesium in this same porphyrin ring is how plants convert sunlight to energy. Here we have phosphorus, which is a key part of the phosphate group in a phospholipid that we talked about earlier. Here we have, this is called a zinc finger, which is part of a larger molecule. These are fairly common structures. So zinc, again, is another mineral that's part of it. So there's lots of minerals. Here's a list of them. We're not going to go through these right now or ever, but just a list of all these different minerals and what they do for our body and why we need them. So in sum, vitamins are molecules that we need for our metabolism to function properly, that we have to get from our diet. Other plants and animals can synthesize those molecules and we can't, so we eat those plants to get those molecules instead. The reason that this happens, they may be molecules that we once in our history, in our evolution, were able to synthesize, but it's very metabolically expensive for our bodies to create these molecules. And if we're getting them in our foods anyway, then why should our body spend all this energy and all these enzymes and everything else that it needs to make to be able to make these when we're getting it? And so we lose the ability to make these. But now, because we can't make them anymore, if you have a diet where you're not getting these because you're eating, highly processed foods and things that may not have these vitamins that we need, you will get sick because your body needs these molecules to do particular functions. So there are 13 human vitamins. 4 of them are fat-soluble, A, D, E, and K. And all the B vitamins and C are water-soluble vitamins. Minerals like iron are also essential for our body to carry out particular functions. Next, we're going to talk about volatile compounds. So volatile means that they're small molecules that can escape into the air easily. So aromas are volatile molecules that can escape from the food and get into our nose, which is how we detect them with these receptors in our nose. And if they can't escape from food, we can't smell them, right? There are thousands of molecules that give foods all their complex aromas, which is part of flavor. This is just a few that I grabbed and put here, vanillin and benzaldehyde and so forth, that have particular components. So like vanillin is the main component of the smell of vanilla. Vanilla is much more complex than that. There's actually a lot of different molecules that make up its smell in real vanilla. If you buy artificial vanilla, which is what most processed foods are made from, you'll probably only be getting vanillin and nothing else. When you cook foods and your house smells wonderful because you have all these wonderful smells, those are smells that are no longer in the food, right? So if you cook food for a very long amount of time, depending on what it is, it might be less flavorful because all of the volatile molecules have already evaporated. So when you eat them, they're no longer in the food to become volatile as you're chewing them and get into your nose and your smell receptors. So we've talked a little bit about attractions today, about bonds. There are 4 major electromagnetic forces between food molecules. Covalent bonds, first one we learned that this is when atoms share electrons, and it's a very strong bond. It's the strongest of all the bonds. Ionic bonds, this is when one atom completely steals an electron from another atom, like in the case of table salt. The chloride ion has a full extra electron, so it has a full negative charge, and the sodium ion has lost a full electron, so it has a full positive charge. And those are pretty strong, so they're full charges, so there is a pretty strong attractive force. Not nearly as strong as covalent bonds, but much stronger than a lot of other forces. Next is hydrogen bonds. This is from the partial electromagnetic charges, like on a water molecule where they're sharing electrons between 2 atoms, and one of them has a stronger nucleus, a stronger positive charge, so the electrons are attracted to it more of the time. So it will give that stronger atom a slight negative charge, and the atoms like hydrogen that don't have as strong of an attractive force in their nucleus, a slight positive charge. And then van der Waals forces, which are the weakest forces of all of them, and these are these very, very weak transient forces that happen with molecules that are what we call nonpolar. So they don't have these hydrogen bonds that they form, but they still have a very weak form of the same type of electromagnetic bond. It's the same electromagnetic bond in ionic bonds. These are just stronger, a little weaker, and much weaker. These forces determine, either in part or in whole, the shape of the molecules. It's the shape and the forces in a molecule that determine its function. And because of these shapes and these electromagnetic interactions, that's how molecules interact with each other and do stuff. It's because of those forces within some molecules, like proteins, which are very long chains, have a lot of these forces going on even within its own molecule. And then between molecules, that's how like enzymes can put together or take apart other molecules because of these strong attractive forces. So this is super important, the shape and the forces in the molecule that determines its function, especially when we talk about proteins. So this are kind of relative bond strengths, just so you can get an idea. Covalent ones are very, very strong. Ionic bonds are much weaker, but still pretty strong relatively. Then hydrogen bonds are a lot weaker. And the van der Waals forces or blended dispersion forces are so weak that you don't even see the line on the chart that I made.